Okay, so remember, and I know you're like, no, we don't, because spring break happened. But whenever we did the alternating series, we did that error bound, and we said the error had to be less than or equal to the next term. Do you guys sort of remember that? Like the n plus 1, like your error is going to be less than that. So we're revisiting this with these Taylor polynomials. So for your Taylor polynomial approximation, remember how the polynomial is, you use it to approximate a value, like a tangent line. It's just instead of linear, it's a higher degree, it's polynomial. F of x would be the exact value. So like the true answer, like you actually had the function itself. The polynomial is the approximation. Kind of like you have a function and then you have a tangent line that you can use as an approximation. Again, it's just it's a polynomial instead. But because it's an approximation, it's not perfect. So you have this part at the end that's the remainder. And it could be like, it could be off by a positive amount or a negative amount. Like your remainder could be positive or negative. But if you absolute value that, that is your error. So what, like, does that make sense? Like whatever you're off by, that's your error. Okay. So here is this theorem. It is what we did with the Taylor polynomials, just with an n plus 1 in it. Like if you recall, we did the nth derivative, and then it was x to the nth over n factorial. Do you remember that? That was actually, that was the class that we did like right before spring break. Remember with the tornado and whatever. So if you compare these, do you see how it's the exact same thing? Oh, I forgot the minus c in there. It's the exact same thing, but instead of n, it's n plus 1. And also you'll notice there's this value z. I'm going to talk about this in just a second, but let's list off to the side here what everything means, all right? N is the degree of the polynomial, and they always tell you that, like do a second degree polynomial or do a third degree polynomial. You're just going to add 1 to that, like you're going to go 1 further. Bless you. C is where it's centered. For these, they center them at 0. They're going to be Maclaurin. But C is where it's centered. And then X is the value that you're plugging in. So like the value that you're approximating. So you're getting an approximation at X equals whatever. And again, they're going to like have to tell you that. So here's the thing with this Z value. And I put a little blurb there. I think I copied that, or I put it like in my own words from the textbook. You can't get Z, like you can't get that value. So what they're going to do is they're either going to give you a workaround to it, or this is what you're going to do. Z gives the maximum value on the interval where Z is in between C and X. You can't get this Z value. That's like why it's an approximation in the first place. So here's what you're going to do. Either they will give you a way around it, like they'll tell you that information somehow, or what you're going to do is plug in C and X, the two values that you do have, and use the bigger one. So you will have C and it'll be 0, and you will have X. You'll plug in both of those, the ones that you do have, like you're using what you have, and then just use the larger one. Or else they'll give you some kind of workaround. That's like your way around that. Okay, but you don't have that number, so you can't get it exactly. So let's try a bunch of these. Just remember, it's the exact same thing we did before, except n plus 1. You want like the next one. Your error is going to be less than or equal to like the next one. So here, in this one, they give us a workaround. They tell us the nth derivative equals this, and you can just plug in n. So they're kind of giving us a way around not having that missing information. Third degree polynomial. You can stay organized however you like. What I usually do is write the information off to the side. Third degree polynomial means that n is 3. We're centered around 0. Again, they just use 0 for these, which is nice, keeps things simple. And we're doing an approximation at x equals 2. Find the error bound. It basically means plug everything into this formula. All right, so this first part, it's the n+1th derivative at z, which we don't have, but they gave us this handy little formula to use for it instead. Here's the thing, we don't plug in 3. What do we plug in? You plug in 4. So you have to catch that. Because if it's multiple choice, they will make one of the choices be if you used 3, okay? So it's n+1. So we want to plug in 4. So 4 squared is 16. 4 + 1 is 5. So that's that first part of the formula. That's this part that I circled here. So they gave us a way around not having z. They gave us this little formula we could use. All right, and then it's x minus c. So that'll be 2 minus 0 to the power n+1. So again, n was 3, so we want 4. You're always doing 1 more. And then over n+1 factorial, so 4 factorial. If it was free response, literally that's your answer. That's it. If it was multiple choice, you would have to break that down. So for the sake of us practicing like fractions and stuff, let's go ahead and simplify that. You would have 16/5 times, this would be 2 to the 4th. What's that gonna be? 16, good, over 4 factorial. 4 times 3 times 2 times 1. 24, good. You may have said that, I just didn't hear you, I'm sorry. Now you can get through that however you want, but I would not multiply these 16s together. I would try to keep the numbers littler. Let's reduce this. These will both divide by 8. So that'll be 2/3. And then I would multiply them. So 16 times 2 will be 32. 5 times 3 will be 15. So again, if it's free response, you could literally just stop here and leave that. But if it's multiple choice, you'd have to be able to simplify it. So it's a good skill to have. We're going to try that again. Find the error bound. Now, this time they gave us this function. We're going to have to find the derivatives ourselves. We want a second degree. So n is 2. Maclaurin means it's centered at 0. So c is 0. And we're plugging in 0.1. So x is 0.1.
Like if I were to multiply 16 together and divide by 5, if I were to put 52.8 over 24 and have that be my answer, I think it would be. I did it like that, so I might be wrong. But
oh, you're off by the tiniest amount. Yeah, so just don't do that. I had to put it in my calculator to check. It was off by like, I don't know. Just don't do that, is what I'm going to recommend. Yeah, I just wouldn't. All right, so wait, second degree, so n is 2, we're centered at 0, and the x value that we're plugging in is 0.1. All right, so the first part of this formula, you want the n+1th derivative. So that would be the third derivative. So we have to do derivatives until we get to the third one. Y'all ready? First derivative. Now I would rewrite this, or if you don't want to rewrite it, you just want to think of it in your brain as 1 minus x to the -1. That's how you want to think of that. What's our first derivative going to be? Good, 1 minus x, and this would be to the -2. Oh, but chain rule, you have to chain on the derivative of what's inside, which would be what? -1. So actually these negatives are going to cancel. That'll be positive. So second derivative, you would bring the -2 down. It's going to drop to a -3. But then again, chain on the derivative of the inside, which would multiply by a -1. So it's going to make that a +2. And then third derivative, are you seeing it there? What's the next one? So -6, good. And then 1 minus x to the -4th, but then you chain on the derivative of the inside, which would be a -1. It'll make that positive. So actually, let's rewrite that one. That'll be 6 over 1 minus x to the 4th. All right, so we got our third derivative. So the first part of this, we want the third derivative at z. We don't have z, and they didn't give us a way around it. So you're going to use what you do have. You would plug in C and you would plug in X, and you're going to use the one that's larger. Thank you. All right, so let's try and plug in 0. We do the third derivative at 0. What is that going to give us? 6, good. And then if we do the third derivative at 0.1, this is why you have a calculator. Go ahead and plug it in. You're plugging in 0.1 right here. And you can shout it out when you get it. Or compare with your neighbor and make sure you all got the same thing. Perfect. Did you get 9.144? Okay. Well, which one's bigger, guys? Yeah, good. So we want this one. So that's going to be the first part of the formula. And then it's x minus c, so 0.1 minus 0 to the power n plus 1. Again, you always want the next one. So that would be to the third, and then over 3 factorial, and you're going to just put that in your calculator. Now, do you have that 9.144 still sitting there? Then you can just reuse that, or you can store it, like do store alpha A, enter, and then reuse it. However that works for you. Here, I'll store it, but you have to reuse it in some capacity because otherwise it's not going to be accurate enough at the end. And then 3 factorial is 6. You do get really teensy little decimals with these because it is really accurate. The error is not that much. Did you get 0.001524? Yeah. Oh, I did round up. Why did I do that? I don't know. I guess because it's so tiny, I wanted to feel like there was something else there. Yeah, I usually do truncate, but these numbers, when you do problems like these, the error is so tiny that I'll tend to even write, like, actually, we're going to get to one problem on here. I think it might be the last one, where I actually do like a whole lot of decimal points because it's so accurate out to so many places that you kind of need to write them all. Yeah, right. Like, yeah, or else it would be like nothing. Yeah. All right, given that, now that we get the third derivative here, which makes sense because it says second degree Maclaurin polynomial. So n is 2, c is 0, x is, let's see, what are we plugging in? 1 for that. Find the error bound. So since n is 2, we want the third derivative. Again, it's always plus 1. They gave us the third derivative, but we don't have z. So we're going to plug in c and x and see which one is bigger. So let's do our third derivative at 0. What would that give us? You plug in 0. That would be 1, good. And your third derivative at 1, be e squared. You can type that in if you want. It's like 7 point something, but for right now, let's just leave it e squared. Which one of those is bigger? Yeah, good. So take the bigger one. So use what you do have and then pick the bigger one. So that's the first part of the formula. And then it's x minus c to the n plus 1th power. So that would be to the third. And then over n plus 1 factorial. And so again, you're going to type that in, get a decimal. That's our answer. It should be 1.231509. What's that? Correct. Yeah, the error was a bit more. Determine the degree. I was going to say something else, but then I changed my mind. All right, determine the degree. All right, so for this one, we don't have n. N is missing. That's what we're trying to find. It says Maclaurin, so C is 0. Again, they just always use 0. What is x? It's kind of hidden in there. They did give that to us, but it's sort of like, yeah, it's that 0.6. They wrote it, the function is e to the x, and then the value we're plugging in is 0.6. So we want the error to be less than 0.001. Here is the great thing about when the function is e to the x. What's the derivative of e to the x? X. And forever after. So your nth derivative is e to the x, and your nth plus 1 derivative is e to the x. So let's just go ahead and write that down. It's going to be e to the x because they all are. Again, you don't have z, so what are you going to use instead? C and x, and then pick the one that's bigger. So if you plug in 0, e to the 0 is 1. If you plug in 0.6, it'll be e to the 0.6, which is going to be bigger than 1. You can type it in the calculator if you don't believe me. Actually, here, let's do that. E to the 0.6 is 1.822. All right, so that's the one that we're going to use. So it'll be e to the power 0.6. What comes next? Good, x minus c. So 0.6 minus 0 would just be 0.6 to the power n plus 1 over n plus 1 factorial. We don't know what n is. That's what we're missing. And we want this to be less than 0.001. Here's where this gets really frustrating, and I'm the messenger. Okay, so don't get mad at me. This is the way it is. You test, well, let me let n be 2, let me let n be 3, let me let n be 4. And so you get a value that's smaller than 0.001. This is fun, right, guys? Go ahead and try. Tip tap in your calculator until you get it to work. Yeah, so if you do 5, here, let me show you back. That's the answer, n is 5. But let me show you what it would be with 4. It's like just barely over 0.001 if you use 4. So you have to go to 5. And yeah, this is scientific notation for times 10 to the -4th. So you're going out another decimal point. Okay, thank you for head nodding. So that's it, n equals 5. When you go back to look through your notes, you're gonna be like, how did we get that? Because it looks like we didn't do any work. So maybe put a note like typed in calculator. Yeah, like trial and error, or write yourself some sort of note, because if you don't, if you look back at that to go study, there's nothing there indicating how we got the answers. So like write a note so that you don't confuse yourself if you go to look back at that. All right, given this really interesting polynomial that has almost no information in it, using second degree Taylor polynomial, so n is 2, and we're not given a value for x, and we're not given a value for c. We're not even told where we're centered, but all it says is find a formula for the error bound. So we're not going to get it exactly like a numerical answer. We're going to find a formula for the error bound. But since n is 2, what derivative do we have to find? Third. Okay, so let's go do that. All right, so first derivative. Now all this a sub 0, sub 1, sub 2, sub 3, those are all constants. So when you do a derivative, that first one's going to go away. And so what would your derivative be for like these other parts? A sub 1 plus x, good, and then plus 3a sub 3 x squared. You're doing the power rule, you just are missing a lot of the information. You don't have any of the coefficients. But what's cool about this is every time you do a derivative, it's going to keep on getting smaller and smaller. So second derivative, this first part drops out. It will be 2a sub 2 plus 6a sub 3 x. And then the third derivative, or oh, you're following me there? Yeah, like they're just numbers, like they're just values. So again, 2a sub 2, that's a constant, that's going to go away. And so we get 6a sub 3. Here's why that's a really good thing. You would have to plug z into that, but we don't know what z is. So you'd be like, oh, well, I'm just going to use x and c. Well, bad news. We don't know what x or c are either. But it turns out we don't have to plug anything into that. Why not? Well, that's a constant. Doesn't matter what you plug into it because it's just a constant. So that's the first part of the formula, 6a sub 3. And then what would come next? Get x minus c to the n plus 1. Now we actually have n. N is 2. So this would be to the third, and then over 3 factorial. What is 3 factorial? I know that they said that, but that's poor. I didn't make up this problem, by the way. It's poorly written on their part. They should have said at a value c, at some value c. Like x and c are not one and the same or interchangeable, so to speak. It's kind of like x is a variable that can represent anything. And you know how like if you're doing a function, you plug in x equals 2 or x equals 3 or x equals 5. That doesn't mean x is that. It doesn't mean x is c. X can be, that's a good way of saying it. It's poorly worded on that part. Gosh, you guys are so smart that it's like, yeah. I love this class. You guys are awesome. But no, we will leave it like that. What is 3 factorial though? 6. So these are going to cancel. And so this is your final answer. All right, one more. And this one's going to be heavy on the calculator as well. So just make sure you've got that handy. All right, for f of x equals sine of x, third degree, all right, so n is 3, Maclaurin polynomial, so centered at 0. And they give us the polynomial. Approximate sine of 0.1. So we're going to plug in 0.1 and determine the accuracy. So here's the thing with this question. We are going to approximate sine of 0.1, which is kind of silly to approximate it because we could just find the actual answer, right? Like, why are we doing an approximation when we can get the exact answer? But that's not what the question's asking. The question is asking, how accurate is the approximation? That's like, what's going on. It's all right, so the first part of it is do the approximation. So this is the polynomial. We're going to plug in 0.1 to get the approximation. Again, it's kind of like if you had a tangent line and you used it to approximate something, it just, instead of linear, this one's to the third. So plug 0.1 into that and we'll get the approximation. And then what we're going to do is talk about how accurate the approximation is. Yeah, and here's where you're going to want to go out a lot of decimal points because it's very accurate. And so it's accurate to like a lot of decimal points. I think I did 7. Well, this one's 3333 forever and ever. Did you get that? 0.0998333333? Store that is A. Do you guys remember how to store? That's a good conversation to have before the AP exam as well, so you know that. Good. Store alpha A equals. Store alpha A, enter. Or whatever letter you want to use, but I would just always use A. All right, that's the approximation. Now we're going to find the error to figure out how much that's off by, okay? So since n is 3, what derivative do we need? We need the fourth. Here's the cool thing about the trig functions though. The derivatives cycle every fourth one. Let's count them out verbally. What's your derivative of sine? So that's the first one. Cosine would give you negative sine, cosine. Okay. So if you want the fourth derivative, it's going to be sine. You can write all those out if you want to, but they cycle every 4. So if the function is sine, the fourth derivative is sine. We don't have z, so what are we going to use instead? X and c, and then use the bigger one. So we're going to plug in 0, and we're going to plug in 0.1. Sine of 0, just 0. And then, so sine of 0.1 is going to be the larger one. We are going to type that in, but for right now, I'm just going to leave it as sine of 0.1. Which again means the whole thing is really kind of silly because that's the actual answer. But we're talking about how much error the approximation has. That's what we're doing. Okay, So let's do our formula for our area. It would be this sine of 0.1 and then x minus c to what power? And remember, you want the next one. Fourth, good. And then over what? Oh, good. You could just say 24, 4 factorial. Go ahead and type that in, and whatever you get, store it as b. I think it comes out to something that's so tiny, it's scientific notation, if I'm remembering correctly. So I'm not even going to write it. I'm just going to store it as b. Oh yeah, everybody needs to be in radians. Correct. And this is the first problem where it would have caused an issue because sine is in there. The whole radian degree thing only matters when you're doing trig. Everything else is not gonna matter. Yeah, did you get 4.15 and then blah, 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 e -7? Like it's teensy tiny number. That means the error is really, really small. It means this is very, very accurate. So our actual answer, sine of 0.1, is going to be in between. Now this is our approximation, and this is how much it could be off by. So on the lower end, it would be that approximation minus the error. And then on the upper end, it would be that approximation plus the error. Does that make sense? Like you can be off by that error amount either above or below. Okay, so we're going to do a minus b. And again, you're going to have to do a lot of decimal points because the first several are all the same because it's very accurate. 0.0998329. And then on the upper end, a plus b. Forgot the 0 again, geez. Yeah, and if you type in sine of 0.1, it will be in between this. So that approximation is very, very accurate.